All right. This is your season recap. Your season finale is going to be on December 8th at 1740 or 5:40 p.m. Um, I think it was at least that's the time that I have because I don't really fit a category. But if somehow that is going to be a problem, email me. Um, at least for now. How your final is going to proceed, I'll talk about that at the end of this lecture because as of right now, I still don't 100% know because I don't know about the departmental final yet. But that will be at the end. Hopefully, we'll see. Anyways, season recap. Basically, so I have a lot of these slides where I just have equations and stuff on there. I'm not really going to talk too much about them. They're kind of there as a guide for help me remember things. But yeah, so don't be surprised if I don't get through everything. It's kind of just drills it into you. But what I will do is that every section I have a question that has multiple parts of it, and my plan is that at least my part of the funnel will look like that. You'll have one from the 3 to 4 sections that we've covered, meaning you had a test over chapter 1 through 5. You'll have a question over that. You had a test over chapter 6 through 10. You'll have a question over that. And then you had a test over chapters, say 11 through 15. You'll have a question over that, or 16 through 17. You may have a question over that. I'm probably most likely going to give you questions over um, the first 15 chapters since they carry over a lot more into physics too. But more on that later. Um, so, chapter 2 was kind of the first chapter because chapter 1 was review. And a couple things that I wanted to point out here is I have a new little writing pad here, so this is going to be weird. Is distance versus displacement. So, if you start off at point A and travel 1 kilometer that way and come back 1 kilometer, your distance is a scalar and it's going to be 2 kilometers. Your displacement, however, is going to be 0 kilometers since you started at the same place. Another difference between distance and displacement is Newton. Oh, I always use Newton. That's a terrible example. York, Nebraska. Oh, do I really know how far York? No, I do know this one. Springfield, Colorado is roughly 310 miles. It's a small town in southeast Colorado. Um, 310 miles, that would be distance. The displacement would be a vector, so I would say 310 miles to the west, and almost directly west. So that's why I chose it. Um, Coming down here, acceleration. It is 9.8, but that's the magnitude. When we do problems, we'll substitute it as a negative 9.8 meters a second squared. Where you see a letter G, that value is always going to be equal to a positive 9.8. So, like in the formula, mg, and if your mass is 100 kilograms, you just take 100 times a positive 9.8 and you get 980 newtons. Now, where it becomes a directional, like positive or negative, would be if that were my weight, then that would be 980 newtons pointing towards the center of the Earth. So G is a positive value. And that's always going to be a positive value. You make your vector positive or negative based off of the situation. But when you have gravitational acceleration, like if you're in a free fall and using this equation, you would plug in negative 9.8. Um, Moving on to the pictures here. On the left, we have displacement versus time. On the right, we have velocity versus time. And couple of instances, both this section right here, um, well, actually not quite what I wanted there, but in this section right here, in this section right here, we do have a speed. In this case, we have a case where we are moving at a constant velocity going up, and here we have a constant velocity going down. But we know it's a constant velocity because the slope of this line is going to be a constant value. And since it's going up, this would be like we're moving away from the point right here to point right here. So you're moving away from the origin. Here to here would be you're moving back to origin. This little chunk right here, since your displacement is constant with time, is your static. Let's use that word. And here you have curvature. Now, we know that the slope of this graph is equal to your velocity, right? But if the slope is not constant, i.e. the slope is changing, then this means that you're going to have acceleration. Specifically, in this case, you'll have a negative acceleration because they're slowing down as time goes on. So there's a lot of different things you could pull off of a displacement versus time graph. The velocity versus time graph over here, in this case right here, in this case right here, these are both instances of having a constant speed. Here, you're actually speeding up, and lost my little cursor there. At this point right here, you are speeding up. And you're thinking, well, we're going down. Why are we speeding up? Well, because remember, speed is a positive quantity. It doesn't matter whether you're speeding up going backwards or forwards. You are increasing your acceleration backwards, so it implies that you have a negative acceleration, but we would still say we're speeding up. And here, since your velocity is... here, you're not moving at all. I mean, I was going to go with something else, but... And that means that you're going to have zero velocity because your velocity is not moving with time, so to speak. And a couple of things interesting also about this graph, this velocity graph, is if you find your area underneath this whole curve, you'll actually get your distance. And of course, when you take your slope, you get your acceleration. So a couple interesting things about that graph. Anywho, there's a lot more to say, but I simply don't have the time to do it, so I'm just kind of hitting the highlighted points. And so you're going to see things that I just simply skip over. Sometimes the equations are there just in case I have a thought. Basically, when I teach this in class, someone may have a question, and I maybe go to that equation, so that's why they have them up there. Chapter 3 was kinematics, otherwise known as projectile motion. I probably used the word projectile motion more, particularly it was in 2 dimensions. So projectile motion. So the most important thing about projectile motion is if it's in free fall, the acceleration in the x direction is equal to 0. And so that's where this little thing comes in, this picture. If you throw a ball up in the air, this represents your vertical velocity, Vy. It will get smaller and smaller as time goes on until at a point at the very apex of the trajectory, your vertical velocity will equal 0. Then your velocity becomes negative as it falls back down towards the center of the Earth. But one thing to note, as I said, the horizontal acceleration never changes. That's why each of these lines are exactly the same length. That's because gravity only acts up and down relative to, say, the Earth's surface. And if you neglect air resistance, which we do, there is no acceleration in the horizontal direction. The reality is there's a little bit of deceleration because of air resistance. If you're going small, meaning you're not going to shoot an object too far and it's pretty heavy relative to, say, its surface area, then it's not going to really be a factor and these equations work. Only if, like, I don't know, let's say I crumble up a piece of paper and try to use that as a projectile. Yeah, air resistance is going to be a big deal then. A lot of surface area. Okay. I think that's all I have down here for this one. So basically I'm going to go through each of these chapters and I'll do a problem that kind of incorporates all of it. At least that's where I'm going with this. Chapter 4, a lot of different things I could say about this, but I'll kind of just go on and on and on. One thing I see a lot that I'll just kind of highlight is This is G. This is your universal gravitational constant. You use this when you deal with like planetary motion. Because this equation gives you the gravitational pull between any two objects. So this is the universal gravitational constant. Gravitational. And that G is, of course, 6.6. I'm going to round it. Make it 6.671 or whatever, times 10 to the negative 11th Newton meters squared per kg squared. Okay, little g is equal to 9.8 meters a second squared. This is just for Earth. That's the gravitational acceleration of Earth. This is the universal gravitational acceleration. Well, universal gravitational constant, sorry, for everything, anything in the universe. And that gives you the gravitational pull between two objects. So don't get those two things confused, because a lot of people do. And so I felt like I should highlight that. All right. Chapter 5, we did circular motion. We had bank turns. We talked about Kepler's law, things like that. One of the biggest things that came out of that is this centripetal force. So if you're swinging an object around in a circle, at any given point, it could fly off at a tangent. Your centripetal force will point towards the center of the circle. Now, you can create a force with a constant velocity. And the reason, sorry, I should really be more accurate, constant speed. What I mean by that is that we know that force is equal to mass times acceleration. So you have to have acceleration, right? And acceleration is equal to the change in velocity over the change in time. But how do you have an acceleration when you're at a constant speed because your velocity is not changing? The answer is that your speed is constant, but you will have a change in the direction of the speed over time. And so it's that change in the direction that gives you the centripetal force. The centripetal force will point towards the center of the circle, same as the centripetal acceleration. It's counterintuitive, but it's the pseudocentrifugal force that pushes you outward. And that's why you have a tendency to fly out when you're in a circle. So that's the biggest thing I wanted to highlight with Chapter 5. Okay, the drawing below shows two forces acting on a happy face. The mass of the happy face is 2 kilograms because that's what it is. I can't make this up. Assume that the happy face is on a frictionless surface. We want to know the magnitude and direction of the net force acting on the face, the magnitude of the acceleration, and the happy face travels a distance of 10 meters. If it started from rest, what will be its speed after 10 meters of traveling? So a lot of at least my portion of the test is going to be like this. I'll have a problem where it has 3 different parts, and then you solve everything based off of that. So scrolling down, looking at my picture here, couple things to note. You have to project your vectors. And so like when we have, well, there's different instances, but in this case, what we need to do is we break this down into triangles. And then we need to find the horizontal component, which I will call AX, and the vertical component, which I'll call AY. The AX horizontal component, since it's in a easterly direction, is going to point this way, and your vertical component will point up, since it's got a northerly component to it. Northerly push, rather. And then we'll call this one BY, and then this BX. The BX will be going towards the right, and by that I meant left as I drew it. I said the wrong thing. And then it also goes down, because the BY goes down because it's got a downward direction to it. So what we got to do is we need to find our net forces. So let's first find the net force in the x. So F net sub x. Um, so we take our AX component, which will be 35 newtons. So that's your hypotenuse. Then your trig function, since it's right next to my 35, that's going to be cosine of 35. I kept that pretty easy, didn't I? And that's going to be positive since it's going to the right. Then I'm going to subtract my BX, which is going to be the 40 newtons. And then it's going to be on the opposite side of the angle of 29. So that's going to be sine of 29 degrees. And I made that negative to account that it's going to the left. And then that's going to be equal to my net force. So let me calculate that. 35 cosine 35 minus 40 sine 29 is going to give me 9.28. So that just gives me my x component. Then we need to do the same thing with the y. And so I take my AY component. So that's going to be 35 newtons. It's on the opposite side, way over here, away from the angle. So that'll be 35 sine 35. Minus the BY, which is going to be 40 newtons. Cosine, since it's right next to the angle, of 29. Putting that in my calculator. 35 sine 35 minus 40 cosine 29. And that's going to give me negative 14.9. I carried out two figures. Let's see, 3 sig figs, close enough. So a negative 14.9 newtons. That means that overall, this little happy face is going to get pushed to the right because of 9.28 newtons, and then get pushed down. So let me erase this to show you. So to get your angle and such, you got to draw head to tail vectors. So it's 9.28 positive, so I'm just going to draw a small line this way and write 9.28 right here. And then it's going to be 14.9 down. And so I draw a bigger arrow since it's 14.9 and write that down. And then so what we need to do is that we need to find this side of the triangle. Because what we just did is we figured out that the happy face is being pushed both to the right and down. And so it's going to be displaced right along this direction. So we need to find our third side, C. And then to get our angle, there's a lot of different options, but we'll go ahead and calculate that angle. All right, so to get my C, we use the Pythagorean theorem. So that'll be 9.28 newtons squared plus 14.9 newtons squared. And of course square root that because that's how you use the Pythagorean theorem. So 9.28 squared plus 14.9, square that, and then we're going to take the square root of that, and I'm looking at, looks like 17.6. Now, if it asks for the magnitude of the force, that would be it. That's all you need to do. Because magnitude just means the scalar value and not the direction. If it asks for the force, that's a vector, so it needs both magnitude and direction. In this case, it says magnitude and direction of the net force acting on the happy face. So now we need to find our direction. And so the easiest way is to take the inverse tan. If I can find my whole thing. There we are. So I'm going to take the inverse tangent of 14.9 over 9.28, and I don't need units since they're going to cancel out. So, oopsie. Inverse tangent of 14.9 divided by 9.28, closing. And that gives me an angle of 58.8. A couple ways we can measure it. That could be 58.8, and it could be south of west, since it's just to the south of west. It could also be a negative 58.8 measured from the x-axis. Or 360 minus that, it's going to give me 302, 301 point, oh, what's kind of weird how it came out. We'll round it to say 302. Or 302 degrees measured also from the x-axis. And that would be if you circled all the way back around. Okay. All right. That gets that part of the problem. And I think I have a third part, and hopefully I have enough room. I do. It says it travels a distance of 10 meters. If it started from, second part, then third part. What's the magnitude of the acceleration? This one's really easy. I just take, I know that force is equal to mass times acceleration. So then I just take my net force of 17.6 newtons. And then I divide that by the mass. What was the mass? 2 kilograms? Sounds good. So 17.6 divided by 2 is going to give me 8.8. Then we do the third part. 10 meters started from rest, what will be its speed? So we know if it started from rest, its initial velocity is going to be 0. We know the displacement is going to be 10, and we also know the acceleration. We are looking for our final speed. And so we need an equation that has v's, x's, and a's. And that comes our time-independent equation. V squared is equal to v naught squared plus 2ax. And so I use this equation because you're going to use it in physics too. Not a lot, but it'll pop up a bunch. And it's useful when you don't have a time. You don't know how long it takes. So that's what we're going to use. We want to find v squared. And we know that v naught squared is equal to 0. So basically we're just going to square root 2ax. So 2 times 8.8 meters a second squared. And then x is 10, I believe. I'm going to roll back up to the top. Double check my work. Yep. All right. 2 times 8.8 times 10 square rooted is going to give me 13.3. And so the final value will be 13.3. One other thing that crossed my mind, this right here, I didn't make it a negative acceleration or necessarily even positive because it just asked for the magnitude, and so I kept it as a positive value. And I kind of mentioned that before, but I didn't specifically state that when it came out. All right, so that's one potential type of question that you'll have. It'll come from chapters 1 through 5, so kind of look over your test questions and such and some of the things I went over in class. And it'll come from something similar to that. All right, chapter 6 is up next. All right, what do I have here? A couple things I wanted to say. Chapter 6 was all about work. A lot of different things that I could say about this, but it's just a little bit too much. But a few things that I wrote down that I want to point it out is if you are... Okay, so work is equal to force times some distance s times the cosine of the angle. If this angle happens to be 90 degrees, then your work is equal to 0. Meaning, if your force is directed downward and your displacement is directed horizontally, let's say you are carrying a TV as you walk horizontally, then no work is being done because your displacement and your force being the gravitational force, are going to be 90 degrees from each other. Another example is if you have like a tether ball and it's kind of going in a circle, you'll have the centripetal force that'll point towards the center of the circle, and then the tangential velocity will be 90 degrees. Also, no work will be done. So in order to have work, the force and displacement must be going in the same direction. And that's also why we have the cosine, is to get the angle. We project the vector so it's going to be parallel to each other. Because work doesn't make sense if they're perpendicular. Moving on down here, we talked about conservative and non-conservative forces. Basically, conservative forces are like, let's say you have a walk or a skate park. Basically, all of your potential energy is converted into kinetic, which is converted into potential, and vice versa, back and forth. The non-conservative forces basically involve friction. I can't take that friction, put it back into the system, and have it recreate the initial conditions. But if it's conservative, or at least very close to conservative, I know that when it reaches the top, the potential energy is going to convert back into kinetic, and then over and over and over again. So that's also something I wrote down there that I wanted to point out. And lastly, is if you have a force versus displacement graph, the work is going to be equal to the area, because it'll end up being force times your displacement, which will give you a Newton meter, which of course you know to be as a joule. More on the Newton meters in a couple more chapters. Okay, chapter 7. Couple things that I wrote down I wanted to point out. Conservation of linear momentum. So this conservation of linear momentum only applies to completely, actually just elastic is really what I want to say, but it does say it work completely. So elastic collisions, that's where they have no friction, like two pool balls bouncing off each other, or it is completely inelastic. That's when they stick together with no friction. Now, we never dealt with friction. You're never going to need to worry about that. But those are the two types of situations where we can use the conservation of linear momentum. And the conservation of linear momentum just says that the sum of all the initial momentums is equal to the sum of all the final momentums, which is kind of similar to our conservation of energy, which was your change in your potential energy plus your change in kinetic energy is equal to 0. So there's a lot of different conservation laws in physics, and this is just one of them, and that is linear momentum. There's also angular momentum, but we'll get there in a little bit as well. And that is all I have down for that chapter. Chapter 8 dealt with circular motion. Basically, these equations are very similar to the equations from Chapter 2. This one is the same as V equals V naught plus AT. This is V squared is equal to V naught squared plus 2AX. They're just replaced by their angular counterparts. So it's not too much of new information. One thing that... mine looks a little bit different. Oh, I see why. I did want to point out is your centripetal acceleration and angular acceleration. So a couple of slides back, I talked about how you can have a centripetal force, or in this case, I'm going to be dealing with the centripetal acceleration, and it's going to point towards the center of the circle. God, I'm really not writing too well on this. So we'll call that AC. You also can accelerate. I mean, that's when you have a constant velocity. But if you're speeding up in a circle, then you're also going to have an angular acceleration, alpha, and you can actually experience up to 2 different accelerations. The acceleration through more like the radial acceleration. So basically, you're turning faster and faster, and then centripetal acceleration that points towards the center. So there could be multiple different types of acceleration that we didn't talk about Chapter 5 that did come into play in Chapter 8. But for the most part, most of Chapter 8 was just kind of learning some of these equations so that you can use them in Chapter 9 and somewhat in Chapter 10 to apply to bigger problems. Okay, Chapter 9. A couple things I want to point out Chapter 9. Now, so Chapter 9 is kind of utilizing what we learned in Chapter 8 and two big, huge equations, in my opinion, that are extremely useful in rotational dynamics, and that is tau is equal to IF. Remember, tau is the torque. Sorry, tau is equal to IF. Sorry, tau is equal to FL. Where this is your force and this is your lever arm, and remember that they must be perpendicular to each other, otherwise it's not torque. And it's also equal to I, which is the rotational inertia, times alpha. These are kind of the two juggernauts of that. The units for torque are Newton meter, but it is not equal to a joule, and that's only for torque. And that's because in order to get work, you have to take the torque and multiply it by the angle it goes through. So really work is actually going to be a Newton meter radian. And so don't confuse those two. A Newton meter for torque is not a joule. So that's pretty important to know. Also, rotational inertias. If you don't know the rotational inertia of the object, you can pretty much guess 1/2 mr squared, and you'll be right 50% of the time. That's because this is for a disk, and a lot of problems use disks. Otherwise, they would give you the rotational inertia, or you'd have to look it up in a formula. If I had a question on the test, I'd probably I'd either give it to you or make you. I don't know which one I'd do, since you have open notes. I probably wouldn't give you the formula. You'd probably have to look it up. Oh, here's my work I told you about earlier. It's not letting me scroll. How sad. So also angular momentum can also be conserved. Angular momentum is instead of the mass times velocity for regular momentum, you have its angular counterpart. So the rotational inertia, which is kind of like your quote-unquote rotational mass, times, wrong end of my pen here, your angular velocity instead of your regular velocity. And so you can sum up all of your initial angular momentums and set them equal to your final angular momentums. Chapter 10 expands on that. Couple things to point out on Chapter 10, the notes that I have here. Hooke's law, it's negative kx, but I think your book just gives you a positive kx. It doesn't really matter too much. The big ones about these wave equations really is a omega and a omega squared. That's your maximum velocity and your maximum accelerations. They occur when, like, your cosine omega t, the whole argument is equal to 1, or the sine of omega t is equal to 1, hence it's going to be at its max. And so, though, a lot of times, if you don't have enough information, you could use the maximum velocity. There'll be some little trick that will tell you to use that. Also to note, I wish my mouse was working, is that your angular frequency is different than your regular frequency. Your angular frequency is 2 pi over the period, whereas your regular frequency is 1 over the period. Regular frequency is in hertz, whereas a angular frequency is going to be radians per second. It's kind of a big deal, bigger change there. And then at the very end, we talked a little bit about deformation and compression and tension and things like that, but that's usually not a big part of physics, so I'm not going to focus too much on that. All right, I revamped this problem a bit, added a little bit of something that you may or may not see, and kind of expanded on it a little bit. Basically you have a ball, and it's rolling, not sliding. That makes a difference. Down a ramp, it's going to compress the spring, and once it's compressed, it'll release it and shoot it right back up. We call this a conservative system because we're assuming we're not going to lose any energy to friction. Okay, so we have a 100-gram spherical solid ball. That matters. It rolls down the ramp towards an uncompressed spring at 1 meter a second with a spring constant of 100 newtons per meter. The spring will compress 9 centimeters before stopping. We want to know the elastic potential energy of the spring, the initial potential energy of the ball, and the height, y, of the ramp. How do we do this? Okay, well, this is the conservation of energy. And remember, the basics of the conservation of energy is that delta K plus delta PE is equal to 0. The change in kinetic energy plus your change in potential is equal to 0 or some constant. An expansion of that I showed you was K naught, the initial kinetic energy, plus PE naught, the initial potential, is equal to KF plus PEF. And that's kind of what we'll do here. I know that it's going to have initial gravitational potential energy since it has a height, so I'll call that PE sub G. And it's actually going to have two different kinds of kinetic. It's going to have translational kinetic and rotational kinetic. Why? Well, because if it was sliding, when we just treat it as a point particle and we just do 1/2 mv squared. But since it's a ball, it's additionally rolling, so it's going to have 1/2 I omega squared. Hence the solid sphere, because we'll have to know the rotational inertia. At the bottom, it's simply only going to have spring potential energy because it will stop, so the kinetic's gone, and it can't go down anymore, so gravitational potential energy is done. So that means I can now solve the problem. It says, what is the elastic potential energy of the spring? Now, I don't need the K naught plus P naught thing that I did earlier yet, because I know that the spring potential energy, PE sub S, is simply equal to 1/2 kx squared. And I have that information. So 1/2 of 100 newtons per meter times x, which is 0.09 meters squared. And that's going to give me we're going to round it and say 0.41 joules of energy. So that answers the first part. What was the initial potential energy of the ball? Okay, so that's where I'm going to have to use what I talked about earlier. I know, looking at this, since the final kinetic is 0, that my initial kinetic plus kinetics plus my potential is equal to my final. So I could say that 1/2 of mv squared plus 1/2 of I omega squared for both the rotational and translational. And then that's equal to our final potential energy of the spring, which has a value already, and that's that looks like something different, 0.41 joules. Okay, and I totally forgot the gravitational energy, which I said earlier, and that'll be PE sub G is equal to 0.41 joules. There we go. I'm going to simplify this part right here a hair. So 1/2 of mv squared plus 1/2 I. So it says it's a solid sphere, and if you look that up, you're going to get 2/5 mr squared, which immediately presents a problem because we were not given the radius. Crap. But I do know that V is equal to omega R. And so I'm going to make a substitution, and I'm going to come down here to do this. So that's going to be 1/2 mv squared plus 1/2 of 2/5 mr squared v squared over r squared. So now the r's cancel. These 2's cancel. We'll still have plus PE sub G, and it's still going to be equal to roughly 0.41 joules. Then this expands. That's 1/2. This will be 1/5. So that's what, 2/10 plus 5/10. That'll 2/10 plus my 5/10 is going to be what, 7/10? Yes. So that'll be 7/10 mv squared plus PE sub G equals a constant 0.41. And so PE sub G is equal to 0.41 joules minus 7/10 times the mass of 0.1 kilograms times the speed of 1 meter a second squared. Calculator. Whoa, calculator's doing bad things. No, we'll come back here. There you go, buddy. All right, so that'll be 0.7 times that by 0.1, and then times that by 1, and I'm going to take 0.41, subtracting, gives me 0.34. All right, so 0.34 joules. That's our gravitational potential energy. Then it says, well, what was the height of the ramp? Well, I know that potential energy, gravitational potential energy to be more specific, is simply equal to mgh. And so I take my 0.34 joules, set that equal to zero point 0.1 kilogram times 9.8 meters a second squared times h, and then I plug it in. So then I take my 0.34, which is already in my calculator, divide that by 0.1, and divide that by 9.8, and I get a more or less reasonable value of 0.35. So 0.35 meters or 35 centimeters, that's a little bit over a foot, which I guess is a kind of reasonable value. Okay, so basically put, I could then, at this point, if I wanted to figure out, let's say, my kinetic energy, I could just, well, actually, I don't have to really do much. I could just plug in the mass and the velocity, and same with my rotational energy. But this is a pretty good problem, at least with respect to conservation of energy and putting together all of the things that we've learned up to this point. All right, chapter 11. A couple things I wanted to point out here. Pressure, gauge pressure. Gauge pressure is different than regular pressure. Let me try to find my cursor here. Because gauge pressure is basically taking the atmospheric pressure and subtracting whatever pressure you have, which I'll call P1, and then that's equal to P2. So it's measured relative to the atmospheric pressure, and it's not the absolute pressure. Pascal's principle basically states that all in a fluid, particularly a water fluid, in water, the pressure is distributed equally throughout the entire fluid. And because of that, you get, because basically if we expand on this, it's F2 over A2 equals F1 over A1, which basically means that the pressure at any given point in a fluid is the same, but your forces and your areas experienced aren't, which is why the Pascal's principle leads to hydraulics and basically lifting heavy objects that we couldn't normally do. Archimedes' principle is generally used for things when they are floating. I think it's really only done, but... And that is the mass of your displaced fluid is equal to the mass of the object. And that was what Archimedes discovered, is with if you have like a bathtub full of water and the man that gets in, the overflow water is equal to the weight of the man, the mass of the man, sorry. Equation of continuity, we kind of that kind of goes a little bit more than we need to, but Bernoulli's principle, basically at a very fundamental level, is that as your pressure increases of a fluid, your velocity will decrease and vice versa. So that's kind of what you need to know from chapter 11. Chapter 12 is kind of a review of what you learned in chemistry. I had a blank all of a sudden. And basically, it's thermal energy. Also, it's expansion and contraction of objects. Conductors and insulators. Remember this little C here, that is specific heat. And the higher your specific heat capacity, the better the insulator. And the lower the specific heat capacity, the better the conductor with respect to heat in this case. We also talked about latent heat of fusion and vaporization. That's when things either freeze, melt, evaporate, or condense. And when you're undergoing a phase change, the temperature of the substance doesn't change, if you recall as well. So those are kind of things you need to kind of remember about Chapter 12. Chapter 13... that's when we talked about black bodies, white bodies, conduction, convection, and things like that. One of the more interesting aspects of this is it kind of tells you about how much a surface radiates of energy. If you recall, we did the problem where I had wet soil and dry soil in a concrete bunker, and the wall felt much colder on wet soil than the dry soil when it was surrounding it, simply because it had different conductivity values. And so that K is what's referring to your conductivity, and that can determine how much heat is going to radiate. So things you need to know from that, at least little things that I wrote down you might want to remember. Chapter 14, that's when we, also a little bit of review of chemistry, that's when we dealt with like the ideal gas law, kinetic theory of gases, internal energy. Things to remember from that is, PV, NRT, PV, NKT, so you don't really see that in chemistry. This capital N is your number of particles, whereas this lowercase n is your moles. So that's kind of the big difference between the two there. Kinetic theory of gases, this is the average kinetic energy. And this velocity, remember, is called the root mean squared velocity, which physically doesn't make a lot of sense. But just know that it's not really the real velocity. And why is that? Because the entire thing is built on a system of particles. Remember, we took one particle and was bouncing back and forth in, say, an enclosed space, and then we built upon that. And then we had to kind of size them all up because we know there's tons of particles out there, not just one. And that's kind of where it comes from. You can think of it that way. This later on leads to internal energy of the gas, which is solely dependent upon temperature, which is kind of interesting. All right, a couple things that I wanted to point out about Chapter 15. Chapter 15 was a lot about thermodynamics, and particularly the 3 laws of thermodynamics, the 0th law, the 1st law, the 2nd law, and so forth. The one we focused on the most was the 1st law of thermodynamics, and that is the change in internal energy is equal to the heat, Q, minus the work done. And there are 2 situations that I wanted to point out that are kind of important to know. If Q, that's the heat, if Q is positive, then this system gains heat. So I'll just write, we'll write the whole thing. System gains heat. So that means we know that delta U is equal to Q minus W. If this is positive, that means your system gains heat, and that means that your internal energy is going to increase, which kind of makes sense. If you think about a turtle on a 50-degree day, heat is added by the sun, it warms itself up, it magically has more internal energy, which I never wrote the U for, but I think you know what I was referring to. And then turtle wakes up because turtle's got that internal energy. Where'd that come from? Heat from the sun. That's a good one. I haven't come up with that before. Okay, and then if Q negative, then the system loses heat. And so basically, if Q is negative, that means your Q is decreasing, and that means your change in internal energy is decreasing. You could think of it as you're hypothermic and you're losing body heat fast. You're soaking wet and the heat's just radiating away from you. You're losing internal energy and your internal body temperature is beginning to drop. Work. If work is positive. If work is positive, then work is done by the system. And so if the work is positive, so delta U is equal to Q minus W. If that W is positive, that's going to be tracting away from your internal energy, so your internal energy is going to be decreasing. This is like running. You're doing work, by the system. The system is you, and you're doing work, and you're decreasing your internal energy because, after you run a marathon, you're probably going to lose the next fist fight you get into because you're going to be a little too tired to be fighting. Not sure why you want to get into a fight after a marathon, but it's what my brain came up with. Can't make it up. Okay. If W is negative, so if the work is negative, and then it's on system, then done on system. And so if it's negative, you can see right here, then it's going to be minus a negative. So your internal energy is going to increase. This is like eating. You're doing work on the system by feeding yourself food. And that food is what makes you keep going. And now you have energy and more internal energy to go out and do some crazy things and go run and get into a fist fight after you run. I don't know. Either way, I think you get the gist of the idea. So those are kind of 4 situations with Q and W, and that's probably one of the more important laws of thermodynamics. I mean, they're all important, but that's the one that kind of shows up more. Moving on, we have 4 of these processes we've talked about: isobaric, isochoric, isotherm, and adiabatic. Your isobaric process is where you have a constant pressure. This is like work is equal to P delta V. You have a constant pressure, but your volume changes, and this is how you can find work. Your isochoric is a constant volume. So I'm just going to write cons vol. It's basically, if you have a constant volume, you increase the pressure of, let's say, a container by increasing the temperature. So one of those old spray cans. Oh, let's do spray paint. Spray paint can. You put a spray paint can and you hold it over a fire, it's going to increase the internal energy. The volume stays constant, but the temperature is inside is going to increase and the pressure is going to increase to the point where it explodes, which is why you don't put a spray can in the fire. That's a nice example of an isochoric process. An isothermal process is going to be a constant temperature, and that is the work done right here, demonstrated by this equation. Because the temperature is included, but it doesn't vary. There's no Ti, Tf, or anything like that. It's just T. So this is the work occurring at a constant temperature. And we talked a little bit about this, but it's not as big, at least not in this class. And then the adiabatic is no heat transfer. And so basically, if there's no heat transfer, I had to find my notes here, that means that delta U, there's no Q, so delta U is equal to the opposite of the work done. And so notice here that its work is equal, and there's a Ti minus Tf, the opposite of what we're used to. Because of that, that's where the negative of the work comes from. It was kind of proven earlier, but kind of offshooted. But yeah, that's what it means. There's no actual heat transfer occurring. The internal energy is directly related to the work and vice versa. We also learned about thermal energy with respect to molar specific heat. That's that capital C right here. And we also learned about, capital C right there. And we also learned about efficiency, Carnot engines, entropy, etc. I could keep talking about it forever, but I'm just kind of trying to highlight the main points here. Chapter 6 was all about waves. You had 2 types. You have transverse and longitudinal. Transverse wave, if you recall, is a wave that kind of looks like this. Basically, the direction of the wave is moving to the right, but the propagation of the wave is moving up and down. That's transverse. It's perpendicular. Longitudinal is like a sound wave. Well, sound wave is an example of longitudinal, or a slinky. And remember, you have like these little pressure amplitudes. I do a terrible job of a slinky, but you get what I'm saying. That's a longitudinal. Earthquakes, longitudinal. Sound waves, longitudinal. A lot of the waves that you see are longitudinal. Transverse wave would be more like electromagnetic radiation or light. Various different forms of wave speed we can find. Your main formula that we use the bulk of the time, which we just used last chapter, is V equals F lambda, so never forget that one. But there are all sorts of different situations, whether you have a constant, whether it's like through a fluid, a solid, and whatnot. Doppler effect is another important one. One thing to note about the Doppler effect, I mean, I have these three different equations here: source moving away from observer, observer moving towards source, observer moving away from stationary, and so forth. When you do this, make sure it makes sense. If I have an ambulance and it's moving away from me, I know it's going to go, well, the moment it passes me from that point on, it's going to go. So what I expect when I calculate it to find my observed frequency is I should come up with a lower frequency because it's dropping as it moves away, or vice versa if it's moving towards me. So that's kind of how I always approached it. I would kind of think, okay, well, what would make more sense with my answer? And then I kind of apply the appropriate equation. So you can use both moving if you wanted to, just by making one of them stationary. But really, as long as you kind of work your way through that to make sure that your answer makes more sense, then it usually works itself out, in my opinion. And then we just covered this, but chapter 17, we talked about linear superposition, constructive versus destructive. If you remember, constructive interference is like where you take a wave and you match it completely with a wave that's directly in phase, and you get a much bigger wave. That really doesn't look like a wave, does it? Yeah, I know. And destructive is if you have a wave and it's going against a wave that's completely opposite, and you get nothing. So you have constructive and destructive interference. And we did problems like that where you have to be at a certain point. Where would you hear no sound? Where would you hear the maximum sound? Remember that will always occur at half the wavelength. Because when you half the wavelength in any of these, then what I mean is if I take these two waves that are directly in phase and I shift one of them by half a wavelength, they'll be out of phase like here, and then they'll give me destructive interference. So remember the rule that it has to be a half of a wavelength. Remember single slit and circular opening are off by 1.22. I didn't prove that. I have before in the past. Not in this class, but in the calc-based class. But it's a little bit different in the calc-based class because they don't cover as many chapters, so you go more in depth. But it's just accept it. It's gonna be a lot easier. And then the standing waves, as long as you use the right equation, is usually okay. All right, last problem. We have a sound wave from a small speaker traveling at 340 meters a second out of a circular hole with a radius of half a centimeter. The speaker has a maximum rating of 5 watts, so maybe your typical computer speaker, roughly. What is the intensity of the sound 1 meter from the speaker? We're going to say that's 1 meter perpendicularly. That does matter. Let me put a little symbol there because I need to be more exact. The wave diffracts at an angle of 45 degrees. What is the wavelength of the wave, and what is the frequency of the wave? All right, so let's start off with intensity. If you recall, intensity is I, and it's equal to P over A. And so we know the power of my speaker is going to be 5 watts. The area. Now, you need to use 4 pi r squared for the area. Why did I do that? Okay, well, let's say we have a speaker like so, and it's outputting sound like so. And you're thinking, well, the first thing you're thinking of is why didn't I use pi r squared? Okay, well, that 0.5 is just for the speaker alone. That's this little portion right here. But that's not what we want to know the intensity. We don't want to know the intensity right at the speaker. We want to know it 1 meter away from the speaker. And so that 1 meter is then going to be away from the speaker, and it's going to be in a circular pattern. And the circular pattern means that the surface area, or the surface that's going to be experienced it at 1 meter, will be the surface area of a sphere, hence 4 pi r squared. That's why I use that. And so then I just take, okay, that's going to be 5 watts, divide that by 4 pi 1 meter squared, and then I get an intensity. So 5 divided by 4, divide that sucker by pi, 1 squared is, 1, and that's going to give me we're going to round it, 0.4. And the units is watts per square meter. And that gives you the intensity. That's how many watts per square meter of intensity you could expect from this speaker. Next part, the wave diffracts at an angle of 45 degrees. What's the wavelength of the wave? This is where we use the sine theta is equal to 1.22 lambda over d. Why that one? Well, it says circular, so we must use the 1.22, so that's where that comes from. And then I have all the information I need to just solve for lambda. All right, so that's d sine theta over 1.22 is equal to lambda equals d is going to be 0.1 meter. Oh, why am I using 0.1? Because that's diameter, and I gave you a radius of 0.5. So I need to make sure it's a diameter. Or width. You can think of it as width. Width is diameter in this case, right? Then we're going to do some signing. 45 and divide that sucker by the 1.22. Let's do that. So 0.1 times the sine of 45, divide that by 1.22, and I get 0.0, we're going to round it, 0.06 meters. Pretty big wave, actually. Okay. And then finally, what's the frequency of the wave? Well, we use our other equation we used a lot, which was v equals f lambda. Okay? V is normally 343 for sound, but here I specifically said it's 340. So when I solve for my frequency, I need to make sure that I use the correct velocity. If no velocity is given, we assume 343 at 25 degrees Celsius. And so I'm just going to use the numbers in my calculator, which is 0.057 for now. So 340, divide that by whatever's in my calculator, gives me 108. Your answer might be slightly off because I just used what was in my calculator. 108 hertz. So, another question where it's basically 3 parts. Your final will have... Okay, so my written final, at a minimum, is going to have 3 questions, each with 3 parts. My plan is to give you 2 hours, and well, no, I was going to give you 3 hours. Okay, it'll be open from 5 to 8. It'll be different from other ones. You'll find it under, I'll probably have a subsection on the left-hand side on Blackboard that'll just say final, and you'll be able to click on the assignment then. It'll be like a written homework where you're going to have to write it out and turn it in. But you will get partial credit for it. So it'll be like written homework where you can get partial credit. And some feedback, which is kind of nice, I guess. But that's how I'm running my final. As for the departmental final, I have yet to hear. Can't really tell you much. But for now, I'm just going to go off of what I know. And then also, you've seen the final review posted. It's been there for a long time on Wiley. That it's good to do. It's a lot of questions. It's not for a grade, even though a score is given. It will not be for a grade. But I encourage you to work through it, particularly if departmental the final is given. But I don't know that yet because I haven't heard back yet. So yeah, you will have a final in either case on Wednesday at 5 to 8. You will be able to open it up, and it needs to be back to me by 8. I'll post another announcement about it soon, but I'm going to go ahead and try to get this video uploaded because I'm a little 1 day late on this. Sorry about that, but I said I'd get it by Friday, and it's going to be there. So that is it. Enjoy your spring. I never saw you to begin with, except for a handful of you, so good luck and kapla.